Good morning, good afternoon, and welcome to another MEscope videos webinar. My name is Mark Richardson with Vibrant Technology, and I'm joined today by Dan Ambre from Spectrum Diagnostics. And if this is your first time joining us, we welcome you. If you are a longtime viewer, it's been a while since we've had Dan with us, and so we're excited to have him back. And today's topic is MEscope videos, common misconceptions. So we've had a lot of folks that are, there's a few misconceptions about, first of all, using videos for one thing, and then specifically using videos, using a cell phone camera to get videos, to capture videos and understand vibrations. So we're going to go into a few of those and take a look at the MEscope videos product. Dan's going to go through a few case studies, one on a pump and one on a giant soybean dryer, a few cases that he's worked on recently. We'll also be talking specifically about some of the misconceptions around aliasing, sampling rates, lighting when you're using a cell phone. So we'll go into a few different things there. We will have time, hopefully we'll have time at the end of the broadcast here to get to your questions. As always, if you have questions, feel free to type them in the go to webinar dialog box there on the right side of your screen, and we will answer those questions at the tail end of the webinar. Incidentally, we are recording this webinar, so if you want to go back and review it, we'll get this spun up on our YouTube site early part of next week, and you can go back and review anything that you may have missed. With that, let me hand things over to Dan. We'll get going here.
Yeah, hey, thanks everybody for showing up. We got some interesting things today, and we got to jump right in. This thing, what we're talking about here on the front page of the presentation is a setup for a pump analysis with ODS videos. And I'm trying to stir things up a little bit. Some people think that we can't get much definition out of really high expensive cameras. I think you can have some, but it's kind of a trade-off. You're seeing to the left here is a pump inlet, discharge going out the top. I got a bearing housing here on the left, and that's connected to bearing guard and a motor. And what we're looking for is what kind of light do we actually have and what do we need? I have a bunch of panels, 4 or 6 LED panels that I don't use anymore. My thoughts are if I can get as good a data with cell phones, I'll use those because they're cheaper and better. And in this case, what we're just about to jump into was how much light do you need? If you have an expensive camera, I have one of those, and it tints the light to a blue part of the spectrum, so it's a cool burn. I'm not sure how they rate these things, but that's what you're looking at. So in the middle of the page there, it's kind of a light blue, and in the background, there's nothing. If I go back and look at the camera, what it's seeing, it's basically, it got a little cropped in there. So, but here's the camera and here's the actual live image off of that. That camera is looking at this coupling, or the pump, side of the pump. I think we had a pitch. Yeah, obviously we have a pitch in there. So it was a severe misalignment going on. But there's all kinds of other lighting and everything that I don't really need the cameras for. It'd be strange if I said all this was gone in the original video. When we cropped it, all the color started showing back up, but there's a lot of detail. This is a dark room. I don't have any, when I walked around with the light LEDs and we're looking for a good area, it was a pretty dark room. With the cell phone, I got a similar look at that. I could turn on my lights and take a picture of it, what I just did. So kind of you could see the setup in the table. Anyway, we'll get a little more into this, and it's I thought it was kind of interesting when I look back on some older data that I had. There was a misconception that came up in the last ODS videos that I did, which was quite a while ago, and they were talking about, can you really get an unbalance and misalignment and belt drives and all that? And I said, yeah, these are the fault. The fault that decides what this list of 12 problems are is a directional phase fault. And there's a little more than that, but the phase is how it moves. Every one of these faults will show up on my vibration periodic table in the synchronous column. And we'll show you that in a minute. But that just means they all have the same frequency signature. It's a high turning speed of the shaft. In the past, I've heard of people, and I've experienced still, that if it's a high 1 times, they're convinced that it's the solution. Go out there and balance it, and you get some guy to balance for a day or two, and he can't do it, and he feels stupid because he really was doing an uncharted water. Their test, they weren't supposed to. It's supposed to all fall in line, and when it doesn't, then everybody gets frustrated. Anyway. This is how it's taught when you walk into a entry-level class or a level 1 class. You try to get more information. So first we have is this trending block, which is we take our machine, we take our data while it's running, we do our analysis if it's in alarm. My tools now, and this is because we have people from all different levels come into some of our classes. You have a high amplitude. It's all at the frequency 1 times RPM must be unbalanced. So you check the phase and it's not. It's like, huh, that's weird. Check again, and you can't get anything to line up right, and you try a different fault, and you can see what's going on. One problem in the frequency domain, but 12 different problems in the phase domain. Okay. As you get into a level 2 class or level 3, you start to pull in advanced tools like doing some time waveform analysis and ODS, and we're actually doing MEscope videos, which is video ODS. Impact, modal analysis. I'm going to show you a soybean dryer in the back that's going to have not my impact test, but it's like an operating modal analysis. So an operating modal analysis is taken when you can't shut the machine down. And then there's some transient tricks we have and some orbit plots and so forth. So once we get into how all this works, routes and so forth, analysis using amplitude, frequency, and phase, and then getting comfortable with new ideas, we'll be out to the races there. This is the vibration fault periodic table. It's described as a logical visual mapping system to understanding vibration analysis as systems thinking. So we have 4 different things we're going to do in here to try to quickly get us down the right path to the analysis. We define our frequency group. We define then the dominant directional response of that group. We perform a quick diagnostic test, and we narrow down the potential faults. The frequency groups are synchronous, harmonic, subsynchronous, non-synchronous, and modulation, and those are these columns on the table, and you'll notice there's a little bit of overlap in there. Nothing's perfect. The directional group is red. That's easy. Red for radial, yellow for axial, orange for radial and or axial. So we can do some, if we have a phase problem, we can see how that's going. I've given away too much already. We have a synchronous problem. Okay, we have a high 1 times peak in our spectrum. That means there's no harmonics in it. There's no subsynchronous. The non-synchronous is gone. There's no modulated or sidebands. All we have is a high 1 times. Okay. This is where we are now. We gray out everything that's not related to this synchronous fault. We get rid of the other harmonic columns and stick with the one that has the overlap for now. But we'll get rid of 2 harmonics, subsynchronous problems, the non-synchronous, except for natural frequencies. That happens for every application. You can have a natural frequency for every fault. And there's no modulation effect. All we have is a high 1 times, and that has to be our frequency group. So we do that, we define the frequency group. We look for the dominant directional response. So we look at our spectrum that we took in the route, and we line them all up, axial, horizontal, and vertical positions, 1, 2, 3, and 4 for the motor and pump, whatever it is. And we look at our data and say, what was the highest vibration? If I say 1 times, or we know it's all 1 times, the dominant direction, red is radial, and we find out that it's yellow. So yellow means in the axial direction. So that's unusual. Usually all our response comes from looseness and unbalance and misalignment and things like that. The yellow group produces 1 times RPM as well, that's in alarm, but it's a different phase relationship, a different motion, if you will. We're going to see what the response is from bent shafts and angular misalignment and cocked bearings, and if we have an overhung rotor or a belt drive, those all react in the axial direction. So let's say we have a high 1 times RPM in the axial direction, and it's on the pump rotor in the axial direction. Okay. So we didn't take those off. But if we have yellow, we can't have radial as well. We're trying to work to one problem. So, but we get good news is we get to eliminate 4 potential problems on the chart. So now instead of 12, we have 1, 2, 3, 4, 5. And we have 12. So 1, 2, 3, 4, 5, 6. So we have 6 yellow direction potentially that will still light up. The next step is in those, the ones left over, we do whatever test is in the upper right-hand corner to see what kind of analysis we do. The diagnostic tests are phase analysis, time waveform, orbit analysis, transient analysis, and ultrasonic analysis. We're showing blocks with phase analysis is what we should do next. Okay, sometimes you'll get 2 or 3 different problems mixed in here, and you can't get rid of them or gray them out fast enough. So we got to do a couple of things. We're going to do a phase test, and we have 4, 5, 6 potential problems that have phase. We're going to also look at the other phase so that we know we've checked everything over. Okay, so it's just a kind of a check off your box type thing of what are the symptoms of phase analysis, and we won't go into that right now. We also go into transient testing. So it is possible this natural frequency can fall anywhere, can be in any part of the frequency spectrum, and many times it's at 1 times or 2 times running speed. And if we fall into that, we're still in the synchronous column. It just gives us a little bit more emphasis on, is it a natural frequency, or does it belong into a bent shaft or a misalignment or something? So we do a transient test. If we don't have any natural frequencies in this range, then we can cross that one out too, and we'll assume that. So now we started with 35 faults, went down to 12, and if we get rid of this one, we still have 12, 11, 10, 9, 8, 7. So we should have, and 6. So we should have 6 left. Okay. After the phase test, it should narrow it down to 1 or 2. Okay, and we can look into it and see what else is happening. One of the things that can happen is we can take our camera out there, which is our cell phone, and put it on a tripod, take about 15 seconds of data, and analyze that. And we'll see if there's any motion that we can see in the 2 planes that we're going to be testing. Remember, it's a two-dimensional camera trying to take video of a three-dimensional machine. So you're going to have to take data in more than one direction, usually a horizontal and axial if you can get them, and vertical is kind of hard to get too. But I've done a couple of things where I'll get up on a ladder and shoot down on the top of the machine so that you can see it, or go up on a mezzanine and look at it from there. Anyway, there's a lot of things you can do. But that's how we understand the periodic table. There's a frequency group, there's a dominant directional response, we do the diagnostic test, we narrow down the potential faults, okay? And if we can't get it after a couple of passes, then we might have 2 problems, or we might have 3 problems, okay? Don't rule anything out until it's completely ruled out. Okay, misconception is these cell phones only there's a slow motion mode inside the video area, and its mode, or its frame rate for that is 240 frames per second, FPS. The misconception that this is too low to capture common rotating machinery faults, and reality is we just looked at it, and so we have 1 times and 2 times in the synchronous columns, and we will have, with just barely within the 120 sample rate, we'll have all these available for a phase analysis. Okay, so unbalanced eccentricity, mechanical looseness, overhung, belt drive, bent shaft, coupling misalignment, cock bearings, and natural frequencies. Okay, there's still a lot to do. Misconception, 240 frames per second is too low to capture common rotating frequency faults above Fmax and of 120 frames per second. So what he's saying is there's an Fmax of 120 that's too low to see what I want to see out at maybe blade pass frequency. There is a solution to that. The solution is something that's already been introduced into the software. It's calculates the alias harmonics. So it's what we have is it'll capture the top 12 phase faults. It includes all the different motors, and it includes the unfolding the Nyquist frequency. So we have 240 frames per second. We're not using it all. We convert that to the frequency spectrum, and we lose half of our sample rate. So we go from 240 to 120. That's frames per second. So we're 2-pole motor is about 3,600 CPM, just under that. So if 4 poles will get not the 4 poles. I'm sorry. It's a 2-pole motor, so it runs at 3,600, just under 3,580, let's say. If I take 2 of those, 3,580 is, not thinking today, 80, no, it's 40, 40 CPM difference. So anyway, I have a plot here of the Nyquist frequency to see what I'm talking about, but we can unfold that frequency response. So I have my Fmax here at, where is it, 31,710. I have a little formula that does this for me, makes it real easy. Our Fmax is a little different from that from this last application. This is from a little fan blower motor that was running at 2,327 RPM. Here's my 2327, and I can see all kinds of blue labels on here where there's 2 times, 3 times, 4 times, all the harmonics of that. So as we walk through here, this catches my eye, blade pass frequency, and then 2 times blade pass over here, but we don't want to get ahead of ourselves. As we're going through here, I have this. This is 5 times blade pass. And 5 times blade pass doesn't exist in the spectrum up to 31,700. So where it exists is way up here somewhere, but we don't see it unless we fold back the Nyquist frequency. So the way this works, we have peaks that show up in our spectrum that we can't understand. If we put this formula together, we'll find out where the folding frequencies are and where those aliasing peaks are. So I can verify that these 3 peaks with the squares are coming from this response above the F max. So I have something above the F max. It's 3 times blade pass frequency, so 15 times running speed. It should show up right here at 28,506. It's an aliased frequency. There's a big peak here. There's nothing there. We're on the other side. But if I unfold this, we'll be able to see it over here where it's supposed to be. If I unfold 4 times blade pass, it'll show up over here. So you can see the symmetry around the F max is the same for each one of these. So I have 3 anomalous frequencies that are showing up that really shouldn't be there. So the real problem in this case is we have a high blade pass frequency. We can't tell much from the video unless the whole thing's shaking, but still it won't tell us a pulse at 5 times. The accelerometer will. So we are getting a high peak. We're getting a lot of energy, so we should be able to see these harmonics show up a little bit better. Okay, there's a misconception that the cell phone cameras cannot sample fast enough to determine a phase shift from the top to bottom of each frame. So they were thinking that the cell phone takes all the pixels simultaneously when it's not the case, which we confirmed, yeah, that's right. There is a little slew to it. The phase shift in the cell phone camera has been calculated to include a phase shift of about 3%. This shift is not a problem, we've deemed, because it's based on a simple phase analysis where the phase of the interest is 30 degrees, or 0 degrees, 90 degrees, and 180 degrees. If we're going to do a phase test, all the things in the first 2 columns of the periodic table, we're looking for changes in the response of 0, meaning they're in phase, 90 meaning they're overlap each other a little bit, and then 180, they're always out of phase. But it could be, you could add in that 3% and it really wouldn't make a big difference. So any phase analysis for this is just how is the machine moving? It's a description that we're going to need when we look at the response, and it is a good summary, I think. I can't remember who calculated the 3%, but it's a little different in every camera. This is that other problem that we were looking at before. This is cell phone camera requires light panels to adequately light the machine. The reality, camera usually has multiple sensors that detect low light. Most of the time, the light panels will not be needed unless you're in a super dark area. But this is a fairly bright area, or no, this is kind of dark. It had 4 or 6 panels shining on it to get a good color out of it. Reality, there's no panels, no electric cores, no batteries, no charging, and no camera flash if you're actually going to use your phone. This high-speed camera was about $8,500, and I bought it early on, and it's a good camera. It's a really good camera, but I don't use it anymore. I do everything as a camera, cell phone camera, and I haven't had any problems yet with lighting or anything. In fact, I don't even take my panels with me anymore. Misconception, there's no advantage to a cell phone camera. There's a reality checklist here of everyone has a cell phone with a video camera in it that can be used. So you've saved the cost of a camera, and the same, I save my cameras now. I went in to get a new model just about a couple months ago, and they asked me if I wanted to give them $5 for the camera, and I said no way. So I took my camera, and now I'm using that secondary camera as my main one, so I can take data with it. Cell phone produces a much better video image. It depends on the camera. They have different lenses on the back, and they have different lighting sensors on the inside. So even some of these cameras can take pictures in the dark. They're looking at the infrared image that we can't see. But I read up on a bunch of this just recently. Artificial lighting, LEDs not required for most applications. Cell phones are much cheaper than high-speed cameras. Cell phones are more protected to the high-speed cameras. Dust, water, and impact, a lot of hard surfaces in a plant. Cell phones have new touchless Bluetooth on and off features. So you try to remove as much vibration due to you as possible. So we put it on a tripod you see here, and we're not holding it. Please don't hold it. The other thing is, don't do any zoom on this. You can zoom in later, and you can crop, and you can do all the whatever you want to do. But if you need to be closer, then move the entire tripod closer if you can. Otherwise, if you zoom in, it wrecks your animations and drives you crazy trying to figure out why. Cell phones have new touchless Bluetooth on-off features, so they give them to you with the tripod, and it's just a little yes/no button that goes to you get it Bluetooth, turn that on, and sync it up, and very easy. And you watch the counter on the phone as it ticks away, and you count off 15 seconds, and that's your data clip. And then you send it to me, and I figure out what it is. So easy to set up. You'll get used to it. Without a tripod, it's a problem. I get a lot of people that send me the useless data. So a couple things, it has to be in slow-mo mode. Has to be the 240 frames per second to get it appropriate for this analysis. Okay, so we lock it in. Might be a good idea to get an app that locks any phone in to the highest frame rate like that. It's really not that hard though, but being consistent is good. I'm going to talk about cell phone video animation in the time and the frequency domain, as well as operating deflection shape analysis. So the time waveform is simultaneously all phases and all amplitudes and frequencies showing up at the same time. Okay. Our frequency discrete Fourier transform is collected from that time waveform, and now any peak that I put my cursor on will be the bearer of all the amplitude and phase and so forth. And I lay on top of everything those peaks, and I can see the dominant response of the cell phone video. We can also do an operating deflection shape analysis. And why would I do that? It's because I can average. If I can't do that in the discrete Fourier transform range, but if I need more background noise in the spectrum to go away, or I just want to clean things up a little bit, I can ask the software to do an operating deflection shape, and it'll come back with overlap processing and averaging with that. So it'll get me about 25 averages, and it really works. It really cleans up nice. We also talked about aliasing. We can go into orders mode, and it'll show us the orders that are at the alias frequencies above Fmax, and it shows us what happens when we open that fold and look at the full range of the video response. So now instead of having a limit at 120, we can have a limit at 240 and see where all those, it'll show up as harmonics. So if there are other things going on, we should be able to detect it, things at a little higher frequency. But remember, if we're doing operating deflection shape, if we're doing discrete Fourier transform, they're all phase related. So don't forget that. If you, we'll move on. This is ODS signal processing and averaging. The top plot is the Fourier transform. Discrete Fourier transform is the 893, 1190, and 1790 at the bottom of this plot. The top of it, they look the same, like they're trying to do something, but they're a little bit different. This is the time waveform, or is it? No, I think it's the phase from the discrete Fourier transform. It cleans up pretty nicely. It's kind of hard to tell, but you don't look at this every day. But the peaks drew in some of the energy. Like there was a peak that was a little, if we looked at this in a log scale, you could see a little bump here. Well, that folded into the peak and it raised it up a little bit, I think. Same thing here. So it does some nice cleaning up of the spectrum. This is, we combine all these together, the discrete Fourier transform, the ODSFRF, and just the time waveform, and we're looking at a couple of them. I believe this is the time waveform, so you can see all the frequencies at, whoops. You can see all the frequencies at once. Now I got to start it over. There we go. So it's bouncing. I can see it bounce on these three I-beams, and it's pitching and stuff. This is, the application here is a sifter. And what it'll do is it'll spin and it'll break up the soybean shells, and the shells will go off in one direction and the beans will go off in the other direction. And this thing actually turns, it's warm inside. I don't know how hot that warm means, but I was standing next to it for a while. It was kind of warm, kind of a bit hot in my estimation. But it comes somewhere down from the top, the shelled beans, they'll go through this and it's a drying process. So it's a slow rolling drum. You must have some grooves in it to carry the beans along. We were doing the vibration analysis and we stood back and got these videos, and these aren't even the good ones yet. You'll see the good ones. So this is a time waveform. This is the discrete Fourier transform, and put my cursor, I believe, on something around 900, and they don't show it here, but right over here you can see how they're out of phase, these two cross beams, and they're not quite getting it here. And the reason for that is I think there's something wrong with the beam in the middle there, is warped. So it's shifting load into here, making it a little stiffer, and it doesn't line up with that. But at one time, here you can see it in here too. At one time, when it was new, I think you'd probably see the same motion on these 4 X's as you're seeing, as you're not seeing now. This is the upper framework. So stood close by and shot upwards, and the color one's going to come on first, or there it goes. And you can see the bending of the beams. It's very interesting. The sifter is on that deck above it, which is a, I don't know, 6-inch slab of concrete. with a machine that's sitting on top of it, and it's eccentric, and it throws the beans and it shakes them and does all kinds of stuff to them to try to break up those shells. And unfortunately, that spinning frequency was the same natural frequency as the truss underneath. This is actually an operating modal analysis. There's a lot of talk about doing this, hitting with a hammer and doing a modal test, but it's too hard. The modal test for something like this, you couldn't get up that high. We had to get some painter poles and put them all together and move an accelerometer around for several hours to map the floor out. But that's what we were getting. This is a time waveform, which it's very similar to that last one. I think I tuned into a mode that was close, but this is all one mode. It's bouncing up and down. There's no flexing in any of the beams. This is what would be a rigid body mode. And I believe that the sifter had some looseness problems on its mounted feet. That's probably putting some vertical bounce into that. This, I can't compare it. This is an ODS. Nope, this is a time waveform. No, it's not. Here it is, discrete Fourier transform. I'll give you the time waveform none next. So where you find ODSFRF is right here. Tells you what your plot is. And this is a time waveform, and we're looking at the Fourier transfer, the ODSFRF right here at 240 CPM, which is just about that eccentric wheel speed. This is the ODSFRF. Had a little slightly different. That was 340. This is 980. And here's where we see that crossing pattern twisting, just like we did before. They're out of phase with each other, but that's a mode shape. And here's a bounce. This is at roughly 982. And there's they're out of phase with each other still. Oop. No, I thought I had another one. Well, I guess we're a little early. I had another color plot. Let me see if I can pull that up. Oh. Okay, sorry about that. I thought I had another case history in here, but I don't. So common misconceptions. What is 1 times RPM? It's synchronous vibration. So there's a lot of different faults that look the same but are behaving differently in different directions, or pitching and pulling. Like if you had a out of line coupling and it's pushing and pulling every revolution, the fault depends on whatever direction it is moving. So it could be a horizontal response across the coupling, or a vertical, which would give you the radial, or it could be an axial response across the coupling. Okay, so you could probably go for some questions.
If you have any questions, go ahead and get those typed into the question box there, and we get those answered. One comment here from Ed. He says, you got a base structure issue big time. That is an understatement there.
Yeah.
I can't believe that thing looks like it's going to collapse.
I hope it doesn't.
Yeah. You know, Dan, we do have a little bit of time if you want to just run through the wizard real quick. Looks like we got about 20 minutes. Do you have something queued up there?
Let me.
Why don't we do that and just
okay.
we can pull up something in there.
Let me see.
While Dan's pulling that up, I wanted to just talk to you a little bit about the naming. You know, some of you folks may have been heard of video ODS videos, and now we're at MEscope videos. We are doing a little bit of rebranding, so we dropped the just to make it simpler. It's MEscope videos going forward. We're trying to kind of match it to our naming convention with the MEscope VES. But now we're just wanting to simplify it, and so now you see here MEscope NXT. This was another one of our this is kind of an under the covers, if you will, naming. So but what Dan is showing you here is MEscope videos, and so this is the product that you could purchase as a standalone product.
See,
you can purchase
I'm going to do
as
this
an add-on as well.
This is the sifter above, and
there we go.
I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It was 20 feet across my grid, and I don't know what deep wise. It was probably 20, 25 feet deep. What this was I couldn't get enough view to see the floor. You know, it's part of the floor is in this corner over here, and I had to climb up on something. So this is one of the support I-beams, and I climbed to get a good angle. I got on the step ladder first, so don't get all excited. But it helped me understand the floor a little bit more. And I had to glue down a bunch of washers to the floor, so my accelerometer stuff would stick. But I also did this overall ODS video. What is it now? Again, now you got me all screwed up.
It's just MEscope video.
Not nice. Okay, I usually take like about 15 seconds of data, but I like I don't know. Let's go 3 seconds or so. Hit next. Here's my grid. So we don't do every pixel down there. We do enough that you would interpolate all these things together. There's different interpolation programs within it. It's really interesting if you're kind of a geek like that. What we're going to do is extract the time waveforms from all of those. So this thing, you know, it can go up quite a bit. I don't want to spend all my time doing that though. So we have 2880 X and Y time waveforms. And we're going to FFT those to do a spectrum. We'll get the time waveforms. We'll pull all the spectrum out, and we should be able to animate pretty quick.
Pat McCarg just weighed in. He said, you might explain the relationship between the number of frames and the frequency resolution.
Okay.
While you're on the screen here, so.
Well, the number of frames, the resolution is what was it? was 1 hertz, I think. And or 2 hertz, 1 hertz. I think it's the scan rate, or the frames per second, is what the what you actually get when, I don't know, hold on a second.
The more frames, the better the resolution.
Yeah, I mean, that's how it usually
It's
works.
simpler, right? All right, so you're gonna put the distance in here now,
Oh,
so we get some scaling.
yeah. So this is just a scaled distance, and I have marks on the floor, so those are my 2-foot marks, and so that's going to be 10, I think, 10 feet. Yeah, I've calibrated boots, so I know exactly what it's going to be. Here's something that's I used to use, and I don't use it nearly as much anymore because the background removal program is really good, and you get stuff like that happens. Your whole floor starts to get ridges and stuff in it. So anyway, I guess it's this way. There we go. Let me fill it back up. But that's a histogram type program that takes out the big amplitudes at low frequency or small amplitudes at high frequency. I'm going to end up doing that anyway. So this is the discrete Fourier transform at the bottom. And I can go in here and put a peak in. This is probably, yeah, 300, 320, something like that. So this, I don't even need to remove the background because this thing is isolated. It was hanging on springs. It was a pretty cool thing. But here's my time waveform. Which is like the whole building is moving, which it is. The frame was not twisting like this. This is like some overlap processing that is going, plus the frame's moving really fast. So speed decrease. And you remember what those beams were doing down below. This thing is moving in the axial direction of the machine, and it's pitching as well. If I go in here, the whole back end with the eccentric pulley in there is shaking them. So it's kind of going in an oval pattern. But that's the whole building motion, looks like. It seems too high a frequency, but they're responding. Yeah, that's kind of amazing. This was.
Can you? Is there a way to? Questions coming in. Can I export time waveforms like I see on the screen?
You can't do it. Is that what he said?
Oh, he's asking.
What are the time waveforms?
He's saying, can I export time waveforms like this on the screen?
Yeah, you can make a movie of it. I'm not sure they. I can find out. That's okay. What are you gonna do? You need like a text file?
Yeah, he's looking. Yeah, is there a way to get a time waveform out as a CSV file or an Excel file?
Yes. I know there should be. I'm not aware of. It's in a different menu. The menus I haven't kept up. Point graphics.
Nathan, I know you're on here. You could type that answer in. And
Well,
or
here's
Pat.
edit the time waveforms. Here's all the time waveforms in there.
Yeah.
but math, transform, measurements.
Save
here we
data
go.
block.
Save data
Yeah,
block.
there you go.
I can, you just want to play with the, does he want me to send them to him?
Oh, no. He was just asking the question if it's possible.
Yeah,
Yeah.
looks like it.
Yeah.
And once you have the time waveforms, you have everything else.
Mhm.
Uh-oh. No, there's one thing I wanted to do. There's
Questions coming in from Bob. I can answer this one. Is MEscope NXT separate from or an option to the current license of MEscope VES? It depends what you have, Bob, what version, but yes, it is an additional option to VES, or you can buy it as a standalone product itself. So I'm guessing you probably just have a 420, and if you want to add the MEscope videos option, which is what we're looking at here, then it is an option. If you got questions about that, we're happy to put you in contact with Dan and/or our sales department as well.
yeah, that's what I heard. It's a lower form of operating deflection shape, along with the ODS videos. I'm saying the wrong one again too. You keep getting me.
Yeah, so if you have an existing license, say you have a 420, 620, you want to add video processing, that's a VES 9000 video processing option, and it's just over 7,000 to add that.
Well worth it.
Yeah, and if you're brand new and you want to just get into MEscope videos and you have no MEscope license currently, you can either get a 440, a VT440, which is a video of MEscope videos, and that's just in under 12K. And if you want to go to Videos Pro, which adds time-based and frequency-based ODS, sweep and dwell animated display of time-based and frequency-based ODSs, you get that for 16.3. So basically you're adding advanced signal processing for the Videos Pro. So
plus you're using your own cell phone, so that helps. And
yeah, you don't have to.
Then you have
not having to buy any extra hardware. Sorry, I'm talking the top of you.
Yeah. Well, yeah. Plus it's a lot cheaper than the other guys. They're close to 30 to 50,000. Something like that.
Yeah.
Mark can afford it. I can't.
I don't know. That's about it for questions. We got a couple minutes here if we have any additional questions. Dan, is there anything else you wanted to run through here on the video? It looks like we've kind of gone through the a full video here.
Yeah.
If there's anything else you want, I mean, you can talk about, you went through a little bit of removing background.
Yeah, I was going to do the beams underneath, but that takes too long. There's a lot of little triangles. Oh, I know what I wanted to do. I wanted to do the ODSFRF. There's in the drop-in menu.
Quick question. I'm sorry, while we're Bob just had a question here. He said, well, if I can use any video from any other cameras like high-speed cameras. So say they do want to use a high-speed camera. Absolutely, Bob. You can use other high-speed cameras and just import that file.
Yeah, you can. It's any cell phone, tablet.
Yeah, Dan was showing that Chronos camera earlier. That one of his first. That was a Chronos high-speed camera that he was using.
I have one. If he wants to buy it.
Yeah, there are a lot of different high-speed cameras out there, and a lot of folks do already have those, and so certainly you can use what you have.
Okay, real quick here. This is
4 or
the
5.
ODSFRF program. There's block size, number of averages, handing window, linear system, but the reference direction, I want to take a point in a direction. There's 898. I'll have to do, since this is, oh, this is X. So I wanted to go X. And I can say accept, and what it's going to do is it's going to tell me, you know, how many overlaps there were and all that stuff. So I hit accept. And it's going through all those time waveforms right now. So now it's an ODSFRF. They pulled some of the data out of the time waveform as well. But this is that big peak that we were talking about at 3. They're, yeah, 320 to 280. So they kind of found some extra energy that around the first peak. That's pretty cool. I haven't looked at that for a long time. I redid it though, so this doesn't move, but I had to lower the amplitude a little bit. Pretty cool.
That's good looking. Yeah.
Yeah. Once you start doing it, when you see all kinds of different problems, and it makes you think in a different way. Because if there was some little tag or something hanging off of this fluttering in the wind, that would be my biggest vibration in the whole place. It's just looking for motion when it goes through that. It's so that's one of the things you do where you eliminate that and turn it into background or try to eliminate it somehow.
Question came in here just now from Steven. Is there a max frequency that MEscope can handle? We would want to do a max frequency of 5,000 hertz.
Not for the videos.
Okay.
You don't want to do that. There's nothing out there that the videos are going to see.
5,000 hertz?
Yeah, there'd be, you know, unless it's some kind of spec.
It must be.
You know, what's the application?
No limitation in MEscope for max frequency. That came from Patrick McCard from Vibrant.
Oh.
So yeah.
He's a hack. No, I'm just kidding.
So that answers your
limitations?
Question. Yeah,
I wouldn't think so.
Max frequency, yeah.
But it'd be like a buzz on top of a buzz. You know what I mean?
Mm-hmm.
This is low frequency.
Yeah.
And it's got a little higher, you know, riding on top of it. You wouldn't even be able to see a 5,000 hertz in there. Well, hertz, it's not hertz, it's seconds, but maybe that's the problem. Going to the frequency domain, so you want to go up.
Way up there.
Yeah, because this is RPM, and it's 7,200. So I don't know.
Just Pat McCarty is asking, is this like for disk drives? If we're trying to get a video of a disk drive.
Oh, I tried that once. Didn't work out too well.
No.
You had to bang it and then get out of the way really quick, and you still had the little Sharpie I hit it with. But I couldn't get I was trying to make it potato chip, you know, that go into that mode shape, but I couldn't do it.
Hmm.
Is that what he wants to demonstrate?
I'm not sure what he's trying to demonstrate. Comments coming in. Cell phone videos can capture frequencies from 240 hertz up to 14,400 Oh, for 240 hertz or 14.4 RPM. Right. So yeah, you certainly couldn't capture this with a cell phone at that 5,000 hertz.
Well, and the
Then you'd have to
native
be using
units of this, the native units are displacement. So as you go up, like even on this right here, as that goes away, that's pretty common.
Hmm.
And if you look at it on a log scale, it drops off, you know, a decade at a time pretty quick.
Yeah.
So there might be something there, but it's nothing that you'd be able to detect or worry about.
No. All right, well, I think that's going to do it. We don't have any more questions here. And I do appreciate everybody joining us. As I mentioned before, this is being recorded, so we'll get this spun up onto our YouTube page. You can find that by just going out to YouTube /Vibrant Technology, and you can download a version of this recording of the webinar today. And stay tuned. We will get another one of these spun up, probably about another month or so, maybe tail end of March. And Dan, I appreciate you joining us.
Yeah, no problem.
If you have any questions for Dan, you can email Dan directly at modalguy@aol.com. If you have any questions for us at Vibrant Technology, you can reach us at sales@vibetech.com. And we'd be happy to help you out with any questions you might have about the webinar, about the software itself, pricing, what have you. And Dan certainly can answer any questions you have if you have any questions about the webinar today. With that, we'll let everybody go, and I take care, everybody, and we will see you next time.
Yep, thank you, everybody.
Thanks.